Hi friends, here in this video I'll be explaining the problem on velocity and acceleration in mechanisms. So let's get started. Now here is the question given. It is said figure shows a 4-bar chain mechanism. Here the 4-bar chain mechanism is given. Angular velocity of the crank OM is 4 radian per second. Means this crank OM is rotating in a clockwise sense, as we can see here, having angular velocity 4 radian per second, and angular acceleration is 12 radian per second square in an anti-clockwise direction. So this is alpha angular acceleration. Then we have to find angular velocity of link Mn, angular velocity of Nt, here this is link Nt, and acceleration of Mn. So these are the questions. Now here this configuration is given. We can see OM is the crank because the power is given to it, and finally the motion would be transferred to the link Nt. So this is a mechanism in which if the crank OM is rotating, then this final driven link, we can say link Nt, would be oscillating about this point T, and this configuration is given. So we can say that the distance between O and T is horizontally 65 and the vertical distance is 15, and then the various link lengths are given. OM is 25 mm, Mn is 48 mm, and Nt is 30 mm. So we have to start the velocity and acceleration diagram for this mechanism by drawing this configuration again. So I'll be drawing this configuration again. The first question is angular velocity of link Mn, then angular velocity of link Nt, and acceleration of link Mn. Into the solution part, step number 1. Is the configuration diagram, and here I am taking the scale since all the dimensions here are given, that is 25, 48 and 30. So I would be drawing it on a scale of 1:1, or I can say that in order to draw this diagram, first of all I'll draw it on a scale of 2:1, that is I would be doubling the scale. And why I am drawing it on a scale of 2:1? So that it looks proportionate here, and scale I am mentioning, that is 2:1. So all the dimensions would be doubled here. Here I am selecting the center O, and the distance between O and T, it is 65 mm. So on a double scale that would be 130 mm. Then this center T is 15 mm below. So on a scale of 2:1, that would be 30 mm. So these are the centers O and T. Then the crank which is given here, actually it is having an angle of 60 degree. So this angle is there, and the crank length is 25 mm. The crank length is 25 mm. So on a scale of 2:1, that is 50 mm. Then Mn is 48 mm length, so it becomes 96 when I take the double of it. So keeping on point M, drawing a light arc. Next, NT is having a length of 30 mm, so that becomes 60. Keeping on point T and cutting this arc. So here I am getting point N. Joining all these points in sequence will give me the required 4-bar chain. This crank OM is rotating with an angular velocity of 4 radian per second in clockwise direction. It is given. And the angular acceleration of the crank is also given in an anti-clockwise sense. That is alpha is equal to 12 radian per second square. And now once I have drawn the configuration diagram, we can easily go for the velocity diagram, and for that the angular velocity of link OM is 4 radian per second. So therefore its linear velocity would be angular velocity multiplied by the link length. OM is given as 25. This velocity comes out to be 100 mm per second. Now converting it into meter per second, that will give me the value as 0.1. So that's the velocity of link OM, and we are going to start with this. Now this velocity is 0.1 meter per second. On the velocity diagram, I'll be taking a scale of, how to take the scale, this I am explaining. 0.1 meter per second. I'll fit it into 6 centimeters so that the diagram looks proportionate. So therefore 0.1 divided by 6 it is 0.0166 meter per second. So this is the scale which is to be used for the velocity diagram. Now by using this scale we are going to draw the velocity diagram, and to start with it, here there are two fixed points O and T, so they would be taken together, points O, T. Then see, the linear velocity is always perpendicular to the link, and here the link is rotating in the clockwise manner. So the direction or the sense of the linear velocity would be taking any point, like for example point M on the link OM, taking 90-degree angle. So this is the direction for the linear velocity of link OM. Since it is rotating in a clockwise manner, the velocity is pointing towards this side. If it would have been in an anti-clockwise sense, then the velocity would have been on the other side, and it is always perpendicular to the link. So the next step which I'll do here is I'll be drawing a line parallel to this velocity, which is showing the direction of velocity for link OM. Drawing a light line. Then since I have taken 0.1 meter per second, that is this velocity value or the magnitude as 6 centimeter, So taking 6 centimeter distance in the compass, keeping on OT and cutting this line. That gives me the point M. So here is the velocity vector for link OM, or we can say the velocity of point M with respect to point O. Then OM and MN are connected at point M with the help of a turning pair. We can say this is a joint which is offering a turning point. It means when they are joint in such a way, when OM moves in the clockwise manner, MN would be moving upward, so its velocity vector would be pointed upwards. For that, I'll take a point anywhere on this link MN, measuring 90-degree angle. So this shows the velocity vector direction for link MN, its linear velocity pointing upwards. The direction is known, but the magnitude is not there with us. So here I'll be drawing a line parallel to this vector MN. From point M, I'll draw a light line pointing upwards, that is the direction for MN. Now we don't know the magnitude where to cut this line. So just for that, we have another link which is NT, and here there is point T. So if we can have the intersection of T with this line, then we are going to get point N over here. So it means the velocity vector for link NT should be pointing from T towards this line. In other words, the velocity vector should be towards the right side. So on this link I am taking any point. Like for example, here we have point N, already we have this. So measuring 90-degree angle, joining it with point N. So this is perpendicular to the link NT, showing the direction of velocity vector for link NT, that is the velocity of point N with respect to point T. Then drawing a line parallel to this vector, a light line. From point T, this line is passed. It is cutting the line which is passing through M at this point. So that gives me point N. And here is the velocity vector for link MN. And this is the velocity vector for link NT. Then I'll make it dark. So here we have the velocity diagram. Now I'll find all the velocities which are given here. We can get it from this diagram. Like starting with the velocity of OM is known to us. So starting with MN. So velocity for link MN will be equal to the distance MN, small mn, into scale. Because here the distances are in centimeters, so we have to multiply with the scale so that we get the answer in terms of meter per second. Measuring this in terms of centimeter, that is coming out to be 4 into the scale 0.0166. Hence this velocity comes out to be 0.066 meter per second. And now when we look at the question, angular velocity of this link MN is asked. So therefore the angular velocity for link MN would be linear velocity of MN divided by the length of MN, and this should be in terms of meter because we are keeping the velocity in terms of meter per second. So denominator, the link length should also be in terms of meter. So it means divided by Mn. Now Mn is given as 48 mm. Dividing it by 1000 would give me the answer as 0.048 meter. So therefore the angular velocity mn would be, for link mn, it is 1.375 radian per second. So that's the first answer. Then the angular velocity for link nt is also asked, so I'll first find its linear velocity because that would be required in the acceleration part as well. So velocity of nt would be equal to small distance nt into scale. Distance nt is 6.2 into the scale 0.0166. So therefore the velocity of link nt will be 0.102 meter per second. After getting this velocity, I'll find the angular velocity of link nt. So therefore angular velocity of link nt would be the linear velocity divided by the link length in terms of meter. So it is 0.102 divided by the length of nt is 30 mm and that is 0.03 meter, and therefore angular velocity of nt comes out to be, I'll write it over here, 3.4 radian per second. So that's the second answer. That is, we have found out the angular velocity of link mn and angular velocity of link nt. Now we have to find the acceleration of link mn. For that we have to follow the third step, that is the acceleration diagram. So into the third step, that is the acceleration diagram. First I'll be drawing a table. The name of the link in the first column, its length in meters, velocity meter per second, centripetal acceleration, which is velocity square divided by link length in terms of meter per second square, and tangential acceleration, which is angular acceleration into link length in terms of meter per second square. So this is the method we have to follow while drawing the acceleration diagram. And how to fill this table, starting with the first link, which is the driving link OM. So first link is OM. Its length in terms of meter, since it is 25 mm, so that is 0.025 meter. Then its velocity 0.1 meter per second. Next, centripetal acceleration, which is velocity v square, that is 0.1 square divided by 0.025, and the answer is 0.4 meter per second square. Now for this tangential acceleration, since in this problem the angular acceleration is given, which is 12 radian per second, so it is 12 into the link length, and the link length is 0.025, so it is 0.3 meter per second square. Now remember, whenever in a problem for a crank, if angular acceleration is given, then we have to find the tangential acceleration. Otherwise, if angular acceleration is not given, we can take the tangential acceleration for the crank as 0. It means only centripetal acceleration is present. Next, after link OM, there is link MN having a length of 48 mm. So in terms of meter, that is 0.048. The velocity of link MN is 0.066. Then this velocity square divided by link length will give me the centripetal acceleration, and the answer is 0.09 meter per second square. Then tangential acceleration is not known, so we have to find this value. So after link MN, there is link NT, whose length is given in the problem. It is 30 mm, so that comes out to be 0.03 meter. Then its linear velocity is 0.102 meter per second. Centripetal acceleration is velocity square divided by link length, that I'll calculate here. So and the answer of this is 0.35 meter per second square. And tangential acceleration is the magnitude we don't have now. We have to find this. Now, once this table is done, we can start with the acceleration diagram. And for that, in the acceleration diagram, we have to start with the centripetal acceleration, and when we see the values here, we have to take the maximum value out of centripetal and tangential. So here I can see that 0.4 is the maximum value. So I'll try to fit this 0.4 meter per second square in 6 centimeters so that the diagram looks proportionate. Therefore, for the scale selection, we can say that 0.4 meter per second square will fit into 6 centimeters. So therefore, 0.4 divided by 6. So when I calculate this, it is 0.066. So 1 centimeter is 0.066 meter per second square. So this is the scale which we have to use in case of acceleration diagram. Then, after getting the scale, I am selecting the points that are the fixed points O and T first. O comma T. Now, we have to start with the first link, that is the driving link OM. Its centripetal acceleration is 0.4 and centripetal acceleration is pointing towards the center. So for link OM, the direction of centripetal acceleration is towards this center. That is the centripetal acceleration for link OM. Now once I know this direction, I'll plot a line parallel to this going in the downward direction from points O and T with the help of a light line. Transferring this line from O and T. Now, this centripetal acceleration was 0.4. We have taken in the scale this as 6 centimeter. So on this line, I'll be marking 6 centimeter distance. So this shows the centripetal acceleration for link OM. Then I would be drawing the tangential acceleration which would be perpendicular to the centripetal acceleration, because just for an example, if we have a centripetal acceleration, then tangential is perpendicular to it and they are going into the same sense. Joining them, that is this hypotenuse, would give us the resultant or the main acceleration. And as we see, centripetal and tangential are in the same sense, so this resultant acceleration would be opposing them. So that would be the main acceleration for any link. Now after getting the centripetal acceleration, how to get the direction of the tangential acceleration? For that we have to look into the problem and see this angular acceleration. It is in an anti-clockwise manner. So if it is going in an anti-clockwise manner, it means the tangential acceleration would also be in an anti-clockwise direction perpendicular to the link. Tangential acceleration for link OM. If it would have been, the angular acceleration would have been clockwise, then the direction would have been opposite. So here I am getting the direction of tangential acceleration which is towards this left side. So for that, already we have here the centripetal acceleration. So keeping the point over this, measuring 90-degree angle, and tangential acceleration value is also there with us. So first I'll draw the light line. Then the tangential acceleration for the link OM is 0.3. So how to fit it in terms of centimeter? For that we have to divide this value by scale. So 0.3 divided by this value, which is 0.066. So the answer is, it is 4.54 or 4.5 we can say centimeter. So I'll measure 4.5 centimeter in the compass. So this is showing the tangential acceleration for link OM, and this tangential acceleration is perpendicular to the centripetal acceleration. Once centripetal and tangential are known, I can say this is point M for us, and joining M with point O and T will give me the main acceleration for the link, or the resultant acceleration. Now centripetal and tangential are in the same sense. This main acceleration would be opposing them, so the arrow direction is over here, and this gives me the acceleration for link MO. Next, after finding the centripetal, tangential and main acceleration for link OM, the next link is MN. OM and MN are connected, so its centripetal acceleration, that is for MN, would be pointing towards the same center, which is O. So this is the direction of centripetal acceleration for link MN. So I'll draw a line through point M parallel to this. That will give me the centripetal acceleration direction. I'll draw a light line through point M. Now the value of centripetal acceleration for link MN, it is 0.09, and again to convert it into centimeter, divide by scale. So 0.09 divided by 0.066 gives me the value as 1.36 centimeter. So measuring 1.36, or approximately we can say it is 1.4 centimeter in the compass. Keeping on point M, cutting this. So this line is showing the centripetal acceleration for link MN. Then the tangential acceleration would be perpendicular to this link, and just to draw the tangential acceleration, what I'll do here is taking 90-degree angle with the help of this point, drawing a light line. This line would be indicating the tangential acceleration, because right now we don't have the sense where this MN or the tangential acceleration would be, and also the magnitude is not known. Next, after this we have another link here, which is link NT, and here is link NT. Since it is connected to the center T, so its centripetal acceleration would be pointing towards its center. That is the centripetal acceleration for link NT. Now once I know this direction, I'll be drawing a line parallel to through point T, because O and T are fixed. So drawing a line parallel to this link NT, and that will give me the centripetal acceleration direction. Drawing a light line. Now centripetal acceleration for NT is given. It is 0.35 meter per second square. Dividing it by scale, which is 0.066, will give me the answer in terms of centimeter. So my value is, it is 5.3 centimeters. So taking 5.3 in the compass, keeping on point O and T, and cutting this. Centripetal acceleration for link NT. Then its tangential acceleration would be perpendicular to this centripetal acceleration. Now perpendicular line can be away or it can be towards this line. So when I pass a line which is at 90 degree to the centripetal acceleration of nt, perpendicular to it, when it cuts this line which is showing the tangential acceleration for mn, we are going to get point n over here. So for that, keeping a point here, taking 90 degree angle, perpendicular line, so this is indicating the tangential acceleration for link nt, and now I can say for mn, link mn, this was the centripetal acceleration. Perpendicular to it, we have the tangential acceleration. Now the direction is known, it should be downward. That is the tangential acceleration for link mn. At these intersections, I am getting point n. So joining n with point m will give me the main acceleration for link mn. Now centripetal of mn is passing through this, tangential is having the same sense, so the resultant acceleration will be of opposing nature, that is acceleration for link mn. Then we have centripetal acceleration of nt, tangential acceleration of link nt, joining point n with t, or we can say O and t are same, joining with it, n and t has been joined. So this green line shows the main acceleration for link nt, and its direction is, your centripetal and tangential are in the same sense, so this has to be of opposing nature from the other side, which shows the acceleration for link nt. So here the acceleration diagram is complete. Now when I look into the question, we have to find the acceleration for link mn, and this blue line is indicating the acceleration for link mn. So I can say from this velocity acceleration diagram, since the acceleration for link mn will be equal to this small distance mn multiplied by the scale, because mn is in terms of centimeter, it is 4.2 centimeters, into the scale is 0.066, because when we multiply it with scale, we are going to get the acceleration in terms of meter per second square, and finally it will be 0.277 meter per second square. So that's the third answer. So whatever was asked in this question, that is completed. And remember, when we are solving this velocity and acceleration by using this graphical method or the relative velocity method, then the answers may vary. No two answers would be same, because we are using the graphical approach. So it depends upon the amount of scale or the values how which we are rounding it off, that the values would be correct. And with this the problem gets completed. At the end, if you'll find my videos helpful, you can like, share, comment and subscribe our channel and share it amongst your family and friends. Thanks for watching.